So chapter 15 is on organometallics, and it is really an introduction, because what's going to happen is we're going to see organometallics again in several other chapters as we learn other functional groups that the organometallics can interact with or tend to be common reagents for organometallic reactions. So this is kind of an introduction as to what is, right? What is the basis of this kind of chemistry. And so an organometallic compound, so the name, if you think about it, organo means it's going to be carbon-based, right? So it's going to be an organic portion to this compound, but there's also going to be a metal, okay? And the interaction is between the carbon and the metal, okay? And so there's going to be specific metals that work better, okay? But we are really talking about either the alkaline metals here or some of the transition metals. And that will be more specific as we go through here, but the focus is on, right, magnesium, lithium, and copper, again, for this initial introduction of the organometallics. But again, there will be some additional metals that can also be involved here, okay? And so the goal of this chapter is to illustrate, right, how these are used in what we call modern synthetic organic chemistry. So what we do now, right, and again, the books keep updating, so there's always a few new things, but these, again, are the reactions that are tried and true. So we'll discuss those, okay? And then how can we do transformations or reactions that cannot be accomplished otherwise, in particular forming new carbon-carbon bonds. Those tend to be very difficult to do. So usually if we want a compound with 5 carbons, we choose a starting material that has 5 carbons. Does that make sense? Because making new carbon-carbon bonds are difficult, or there's not as many synthetic options for that. But the organometallics, and we'll talk about how that's done, is an option for adding additional carbons. So that's something that is, a little bit difficult to do, okay? So we're going to focus on those reactions. And there's more at chapter 24, which we don't quite get that far with this course, but it is in your book, and if you have a particular interest on this, you can always see some additional reactions on there. And that chapter is on conjugated systems. So usually these reactions will work, with that class of compounds. So this is again, just an introduction right now. So probably the most common or, well-studied of these organometallics is known as the Grignard reagent. This is right up there. And this is organomagnesium. Okay, so that's the bond is between carbon and magnesium. And it is, the way you make it is by taking, right, in this case it's bromine, but it's really a halide, okay, with a carbon chain here that you want to introduce into your new synthesis. And what happens is you react then with magnesium, and this is usually magnesium, the metal. So in the lab, we're going to do a lab like this where we make our Grignard, and we're going to use ribbon, magnesium ribbon. So you actually use the metal, magnesium metal here, solid, okay, in ether. And then what you get is this magnesium bromide, okay, which is really a salt. Okay, so again, we'll discuss what's the value of that. But this is actually an ionic interaction. And this is the one we're going to do in the lab, actually. It's bromobenzene, reacting again with magnesium ribbon, so it's the solid, the metal here in ether. And what you get is phenyl magnesium bromide. And that would be your Grignard reagent that you would then use to carry out your synthesis. And you can do this with alkyl, so, carbon single bond, okay, aryl, so you can do it with benzene, things like that, okay, or vinylic double bonds. Okay, so a variety of different groups can be, part of this synthesis scheme. Okay, so there's going to be other Grignard reagents that are specific, say, to double bonds or specific to having an oxygen present, things like that. But the Grignard reagent is really a general type of reagents. Okay? So what happens here? So why do we have to have ether? So ether is the solvent that must be used to make your Grignard reagent. And the reason is that magnesium needs to be coordinated, which means that if it was just in solution by itself in a different solvent, okay, it would not necessarily interact with the carbon in the way that we need it to. And so what happens is this is diethyl ether, and this is diethyl ether, the solvent, and it actually coordinates, okay, or basically solvates, right? We saw this word with water, but it can also happen with other solvents. But basically, the solvent is interacting with the magnesium and kind of trapping it in a certain position. And then what happens is you can form the bond with the carbon, and then you can also form the bond with the bromide. Otherwise, what would magnesium prefer to do? What do you think? Just interact with the bromide, right? So if the bromide is the ion in solution, right, the magnesium is going to just interact with that. It's not going to really want to interact with the carbon if it's just free in a solvent. Does that make sense? So you kind of need to have this interaction between the ether and the magnesium. So that's why it has to be done in ether. Doesn't work very well, okay, if you use other solvents. Okay? And remember that magnesium, right, is a positive ion, is a cation. So that's why it would prefer to interact with just bromide, right, the negative ion. So that's really the reason here. Okay? You can also use lithium as another option. Okay, so again, lithium is over here, right? It's one of the alkaline metals. And you can have organolithium reagents as well, so you see very similar, right? You take the halide, alkyl halide in this case, and then you add the lithium, okay, and you do, right, a substitution here. Now notice this does not require, okay, ether, so pentane is actually a non-polar reagent, right? Pentane is just 5 carbons, it's an alkane, alkanes are non-polar, all right? And what you get is just 1 lithium, right? But you get 2 to start with because the other lithium is going to form the salt, lithium chloride. Okay, notice that in the, right here, the bromide sticks together with the magnesium. Does that make sense? So again, for the Grignard, this is required. For the lithium, the halogen goes away as a salt. It's a completely, separate interaction. Does that make sense? So that's why you have 2 lithium. Okay? Now the lithium compounds, I have it here in red, they're highly reactive. They're a very strong nucleophile, and we're going to see why in just a minute. Give you some numbers on this. But what happens then is that they react rapidly. So if you're a very strong nucleophile, you're highly reactive, which in organic chemistry, part of it is having a good reactivity. But what happens if you react too much or you react with anything? Then what happens to your yield? Also goes down. Does that make sense? So it's hard to control something that is too reactive. So for instance, the organolithium, compounds will react with oxygen, they'll react with moisture. So if your solvent isn't completely dry, or if you're doing it, in the presence of oxygen, you can, end up with all sorts of side reactions, which again, unfortunately, that's not good for yield, so we don't tend to see as much of this done, in general, because you need to have an inner nitrogen. So for instance, for us in our lab, we can't do that. So if you were doing this reaction, you would have to have a hood. That hood would have to be sealed off. Have you ever seen this in like maybe YouTube or movies or whatnot? Like you have gloves and you put your hands in the gloves, and then it's like a completely closed off hood, right? And they fill that whole hood with nitrogen. So they remove all the oxygen, and so you can do reactions inside of these hoods. We certainly do not have a way of doing that, right? Because everything we have open. So every time you open it, oxygen gets in, right? Moisture, we're unfortunately in South Carolina where it's very, humid. So it is very difficult to do this. So it's not as convenient. Doesn't mean you cannot use this reagent, but let's just say it's not as commonly used. Does that make sense? Do you understand the kind of reasoning? So we want something that's a good nucleophile reactive, but we don't want something that is too reactive either, because then we cannot control the reaction products. Okay, so why is there this difference, right? Why is magnesium all right, a good reactive, but not too reactive? Why is lithium too much? And it really has to do with the electronegativity between the two atoms, the carbon and then your metal. And what that really, the measurement here is how ionic is that bond. Okay, so if you look at lithium, the difference is 1.5, which gives you an ionic character of 60, which is pretty high. Okay, magnesium is a bit lower. Okay, and so having less of an ionic character is actually beneficial. Again, right, there's still plenty of reactivity, but not too much. And the other metal that we're going to discuss is copper. So you can see that copper is 0.6. So there's a much, much lower. And copper, actually, you have to form 2 bonds to the copper. So we'll discuss that as well in order to make that reagent. So does this kind of make sense a little bit? It really has to do with the fact that lithium is more, right? It's going to have a higher electronegativity difference. So it's more ionic than magnesium, which is more ionic than copper. And like I said, we don't really discuss all of the options, but all of these ions are a possibility for different organometallic catalysts. These are the more common ones. So the polar bond. And why again, right? So if we are talking about this ionic character, what is going to be happening then within my molecule? And what happens is that, and this is showing you the magnesium one, but it's really true for the lithium as well. Okay, so the same thing is going to be happening. What we really want is to make a nucleophile. Our organometallic is our nucleophile in our reaction. So what kind of reactions are we talking about then? Out of our 5 different kinds, which kind is this? If you need a nucleophile, it is a substitution, right? A nucleophilic substitution, to be precise. Okay, but it's the only kind of substitution we learned so far, but there will be other kinds of substitutions coming up. But it is a substitution, so what am I going to try to do, right? Is to replace, right, this bond with your ion, and then that ion is going to make my carbon actually the nucleophile. So how does that happen, right? We usually think of carbon as a cation, right? A positive charge. So far, that's what we've seen. But in a few instances, like the alkyne anion, the triple bond, we've seen this, right? So there is a precedent for this. In the cyanide, we can also see this. So it's not that we haven't seen or that it doesn't happen otherwise, but this is a way of doing this, making carbon an anion, right? And again, if you have a negative charge and a pair of electrons, that makes you a good nucleophile, right? Usually nucleophiles are represented like that, right? So this is, again, another way of having carbon as a nucleophile. We've learned a few already. Okay, which I put up on the board here. So this is really the key, is transforming your carbon into the nucleophile. Usually it's the other way around. The leaving group leaves, right, and then carbon is left as a cation, which is the electrophile, and then something else comes along and bonds to the carbon, right? So the nucleophile is this something else. But now I've converted my carbon into the nucleophile. Does that make sense? So this is very useful. And again, this is not just substitution based. We're also going to see some additions. But again, we need a carbonyl-carbon, a C double bond O, which we haven't done those groups yet. So we're going to see how we can use these organometallics in additions later. But right now, these are substitution based. Does that make sense? When you convert that nucleophile. But when we get into the aldehydes and ketones, which should be our next chapter, chapter 16, we'll revisit the organometallics then. Okay, so that's what we're trying to do. Again, does everybody understand that now the carbon is the nucleophile? Okay, so that's how we're going to use it in these. So, okay, so this is what would happen, right? So here's a example what might happen. So you can take, right, your Grignard and put it in, say, water. Right? So what is going to happen here then? Well, if you can see, and you see all these pKa's and weak acid, weak bases, it actually can undergo an acid-base reaction as well. So it's not just a substitution, but these are considered basic. Right? Remember that nucleophiles can also be good bases and vice versa. Grignards are actually good bases, strong bases. And so if you put it in water or another acid, this is going to undergo an acid-base reaction. So it's another reason to do the reaction in a solvent like ether, right? Because ether does not have a proton, so it cannot interact with the Grignard as an acid-base. Okay, so again, if you have moisture, you're gonna lose some of your yield because it's gonna undergo an acid-base reaction. Okay, so the hydrogen from the water, right, would go with your Grignard, with the carbon part of your Grignard, and then the salt, right, would fall apart. Does that make sense? So this is something that can happen, but it is not what we want to happen, right? This would also, again, if you have any, right, protic type solvent, so this is an alcohol which also has a hydrogen, because the Grignard is a strong base, okay, it's going to go towards an acid-base mechanism and remove the proton. Okay, so again, you'll get the alkane, and then the salt, right, falls apart. Does that make sense? So, and this is not really what we want to happen, but it can happen as a side reaction. So what do we want to happen? Well, we want, again, your carbon to act as a nucleophile. So something that we've seen, right, recently are epoxide ring, or oxy ring, right? It can be attacked by nucleophiles. Remember, in a lot of the reactions that were on that daily challenge today were nucleophilic reactions. And so you just had to figure out what was the nucleophile that attacked. That's really, you know, part of that exercise. So in the case of the organometallic is the carbon. So this carbon here, right, the electrons associated with it are going to attack the ring. Remember, the ring opens, right? And then what you have then is you've attached, right, 1, 2, 3, 4, right, 1, 2, 3, 4 to your 2-carbon oxygen pattern. Remember, we also did that at the end of chapter 11, so you always end up with the carbon-carbon oxygen when you have the nucleophilic attack. And so you add carbon to your chain, which again is something that is not that easy to do. But of course you also have the ion, so the ion gravitates towards your oxonium ion, right, or your oxide, oxide ion. Okay, so it's magnesium alkoxide here. So you would have to finish this reaction by getting rid of the salt, which means you add the hydrogen. So where do you get hydrogens from? But from acids. So this is a weak acid. HCl in water is a dilute acid, and then you would get the hydrogen to form the alcohol, right? That's usually a common product of the epoxides. Does this make sense? So again, the carbon is acting as the nucleophile. So it's a new carbon-carbon bond, right, between these 2 carbons. That makes sense? Because carbon here is the nucleophile. And you always, again, make the chain 2 carbons longer. So you can think about it this way, because you always get 2 carbons from the epoxide. So you can think about it either way. Okay. So this is another example here. This is, right, if you think about it, what kind of mechanism is this, right? The nucleophile attacks, the ligand group leaves all at the same time. That is SN2, right? So it is a substitution reaction. And so again, right, the carbon is the one of the ring here, right? That's going to be attacking here. So again, you get that carbon-carbon bond, and then you get the 2 here, right? 2 carbons, excuse me, 1, 2. And of course, this other carbon is because there's a methyl attached. And remember that the nucleophile always attacks the least substituted side, right? this side has 2 hydrogens, this side has a methyl and a hydrogen, right? So you're going to attack the side that has more hydrogens. Does that make sense? So remember, that's a rule that we talked about with the epoxides. Where does the nucleophile attack? It is, right, specific. Yeah.
Where has the most or least hydrogen?
The most hydrogens, which is also considered the least substituted. Substituents are carbon-based, so this has more substituents than this side. So the word, the term more substituted has to do with more carbon chains. The least substituted side has to do with more hydrogens because there's less carbons. So does everybody understand why this is the more substituted and this is the least substituted? Substituents have carbons, right? So the more carbons you have, the more substituted you are. And then again, you get the salt, right, with the oxide, but then you add your dilute acid, and that gives you the alcohol. Does that kind of make sense how this works? So you have the organometallic nucleophile attacking. Again, the less hindered, less substituted side gets attacked always. It's a rule we talked about chapter 11 as well. Clear as mud? That makes sense? Again, we're trying to figure out, right, what kind of reaction is this? This is a nucleophilic substitution. So what you have to keep in mind is that what is the nucleophile? Your Grignard. And you have to remember that it's not the magnesium, it's not the bromide, right? It is actually the carbon that is the nucleophile. Does that make sense? Yes. Because that's really the key. Once that can click, all these reactions are the same. All right, so these are one type, right, or the organometallics, the Grignard and the carbon lithium. Now another option is called the Gilman reagent, and I think I got it wrong here. It should be Gilman 2Ls. So it's named after Henry Gilman from Iowa State University. So he was the one that proposed this particular reagent. So sorry, it should be 2Ls up here. And I think down here. So missed an L there, but basically it's named after this chemist. And this particular reagent has a lithium and then 2 organocopper. So again, remember, copper is not quite as ionic, right? The character was much lower than lithium and magnesium. So this is a little bit different setup. So let's see what this looks like. So you again have your carbon chain. Okay, first you have it attached to the lithium. So how did we get this?
From the reaction beforehand.
So the reaction beforehand, which was?
The halide.
The halide, right? This would be the halide. You would react with 2 lithium, and that would give you, right, your organolithium. So this case is butyl, 4 carbons, lithium. And then you react that with copper iodide. Okay, and again, an ether, so a dry, right, solvent, a solvent that is not protic. And what happens is you have to have 2 because you get 2 of the carbon chains attached to the copper. Okay, and then the lithium replaces the iodide, so it's a copper-lithium product, right? The extra lithiums then go with the iodine to form the salt. Okay. So even though you have 2 alkyl chains, only 1 is going to react. Okay. So copper, lithium, right? And it's di because you have 2 of these alkyl groups attached, but only 1 is actually going to act as the nucleophile, right? Because the nucleophile is what's going to attack, and only 1 of those 2 groups is going to act as the, excuse me, nucleophile. All right, so how does this work? Well, we couple this reaction, so this Gilman reagent with a double bond. So usually that's how, okay, it's just showing you how to make it again. So you have your you have your halide, right? And then you add lithium and pentane, right? Then you add the copper iodine. So this is your Gilman. It's just giving you how did we get to the Gilman. All right, so then what you react the Gilman with is with a alkene. So notice that you have to have a double bond now. We didn't have to do that with the Grignard reagent or the organolithium. But for the Gilman, okay, this is going to react with an alkene, right? And it's going to have, of course, a leaving group associated, right? So is this still a substitution? An addition reaction would do what? What would happen to the double bond if this was addition? It would open, right? Is the double bond affected at all?
No.
Not at all. So this is still a substitution reaction, right? One of these is your nucleophile, just one of them. Okay, so this is the carbon, right? Because this is the bond that's forming my carbon ion. So this carbon is going to attack, right, this carbon, and then the leaving group is going to leave. Does that make sense?
Why?
Because this is the carbon that has the leaving group. This carbon doesn't have a leaving group, and this carbon doesn't have a leaving group. So it has to attack the carbon with the leaving group. Does that make sense?
It's the one that'll have the cation. Yeah.
Well, this is going to be a SN2, so it's not going to be no cation here. But the concept is the leaving group, right, leaves. So this has to attack the carbon that has the leaving group. So this is also SN2. So the key here is you have to keep in mind that this only occurs when you have, right, an alkene. You have to have that double bond. Okay, so again, the double bond is retained, right, and only one of these groups reacted. Okay, not both of them. And then the other thing about this reaction, the Gilman, is that whatever your stereochemistry is of your starting material, so in this case, this is E. Okay, so the double bond is E based on the starting material. The product retains that. It stays in the E configuration. It does not invert, right? Which is something we see with SN2 reactions. But in the case of the double bond, it retains. So if it started E, it's going to end E. If it started Z, it's going to end Z. Does that make sense? So you do want to maintain the double bond configuration. Okay, the reaction is stereospecific. Retains. Okay, and again, just one of the groups, again, this carbon, right, is going to attack which other carbon? The one with the leaving group, right? Does that make sense? So I added it here. This is the new bond, right? Because this carbon attacks this one because it has the leaving group, right? Does that make sense? So I'm adding basically where the iodine was, I'm putting in my carbon chain. Does that make sense? No? Tyler says no. Like, can you tell what a nucleophile is? I guess that's the first thing. Can you look at this and say, yeah, that's my nucleophile, and figure out where the pair of electrons are? That's really the first thing. You have to look at this and say, okay, I know it's between my metal and the carbon, right? That's where that, that sweet spot is, where the carbon is going to turn into a carbanion. It's not over here, right? It's not here, it's not here, right? It's right where you have the interaction. So that means that the electrons have to be here, right? So this is going to attack whom?
Yeah.
Whoever has the leaving group, right? Does that make sense? So this happens every single time with these organometallics. Does that make sense? So what if I had this? Who's attacking whom?
Carbon.
So what's the nucleophile? The carbon, right? Does that make sense? And then it's going to attack, again, whoever has the leaving group, right? So what if I had this? Who is going to attack who, right? I mean, it's the same reaction, right? It's going to be this one here, right? The one attached to the lithium. And again, who is it going to attack? Whoever has the leaving group, right? I mean, it's really, that's the key. It looks like I'm teaching you all these new reactions, but I'm really not, right? And if you use logic, then every time you see this, it should click as to what you're going to do instead of memorizing, right? Just memorize each of these as an individual reaction. They're really not. And we've done, so, right? Who attacks who? Right? Like I could put an OH over there. That's still a nucleophile, right? Who is the nucleophile going to attack?
The one.
The one with the leaving group. Does that make sense? I mean, it is really all the same. I'm not really teaching you any new reaction. I know it seems like I'm not doing my job, but it's like it seems like you're learning all this new stuff when you're not. When you're supposed to be figuring out, right? I already know something, and I can connect this knowledge to something I already know, and that's your nucleophile. So you have to figure that out first. So whenever you look at a reaction, what should you do first and foremost? Find the nucleophile. Then you find who? The leaving group, right? And then the reaction is obvious. It can only happen in one way, right? The nucleophile attacking the carbon that has who? The leaving group, right? So you don't have to be paralyzed just because it looks really funky with all these metal things and there's two of them and right? Oh my gosh, what do I do? No. I already know exactly what to do. I'm going to look for the nucleophile. I'm going to look for the leaving group. And then I know that the nucleophile attacks the carbon that has the leaving group every time. That makes sense?
Yeah.
Yeah. Yeah. Yeah.
Yes.
And I have no idea where I put my clicker thing. Does anybody see?
Is it right here on the
It's behind the it's hiding. All right. So a variation on this Gilman reagent is to use it as a catalyst, so in a catalytic amount. Okay, and so this is how some, for instance, just as an example, I added this here. So this housefly pheromone, this is how you actually make this. So I just, this is a synthesis that the book discusses as like a aside from the reading, so if you want to read more about it, but it can be produced in large scale. So again, if you look at this, this looks, whoa, right? But what am I going to have to figure out? Who is the nucleophile? All right, the one with the magnesium. So what carbon? What carbon is the nucleophile? And this one is drawn a little funky, so I give that to you. You might be like, what? But which carbon? Right? So this is actually, right, CH3, CH2 times how many? 4, right? So I know this does look a little funky, but again, if you drew it out, right, hopefully then you know, okay, it's the carbon right next to the metal, right, which in this case is magnesium. And then who is it going to attack? Again, it looks crazy, but look at the other molecule. Where is it going to attack? Right? This one right here. Why? Because I identified LV, right? My leaving group. Does that make sense? And so then I look at my product and I say, did it work? Right? Again, you know, because they drew it all, they're trying to draw a very big molecule a little smaller, right? But I'm going to add 1, 2, 3, 4, 5 carbons, right, to the 8 I already have. Does that make sense? So hopefully, does that make sense though? So again, I mean, it looks very intimidating. I can see that, but it is not, right? If you ask the right questions. Does that make sense? So, and again, the mechanism is a bit unknown. We don't know all the steps in this synthesis, but we do know how the Grignard is used. Okay, It does only occur if you have the copper iodine, though, as a catalyst. So we know there's something here that's between a Grignard and a Gilman. So we are not, the scientists or chemists are not completely sure how this all comes to be, but basically you can see that it makes sense if you figure out, right, that this is a substitution reaction and you can pinpoint your attack point in your nucleophile. So people are studying this, though. They really want to come up with a mechanism that makes sense. So, all right, so what other kinds of reactions can we do? So we can use, again, the Gilman with the epoxide. So we hadn't seen those two together, right? So we saw it with the double bond. But you can also use the Gilman. And then again, right, the Gilman can have a variety of different groups in that, right, that it can transfer over to the epoxide. In this case, is a vinyl, right? So you have the double bond there. But again, if I look at this, what's my nucleophile?
That one.
This one, right, the CH, not the CH2, right, the one that's attached to the copper, right? So that's going to attack where? This side or this side of the epoxide? This one, right, because it is less hindered. There's a big old thing over here that blocks my access. Does that make sense? So that's why you end up with the bond on this side, right? Yeah.
How'd you know that's allylic? The CH2 OCH.
This one?
Yeah.
This is not allylic. This should be vinylic.
Vinylic, yeah.
Allylic has one more carbon. You can just say it's an alkenyl too. You don't have to get specific, but 2 carbons with the double bond.
Oh, it's just that.
Okay, so again, the less hindered attack. So you can use the key here is you can use the Gilman also with the epoxides. And then the other things, kind of switching gears a little bit in this chapter, is another way of forming carbons with a pair of electrons. Okay, these are called carbenes. Okay, so carbenes. So they are carbons again, right, with an electron pair. Okay, so they would also act as a nucleophile. Does that make sense? So it's just, it doesn't have the ion associated with them. So this is the simplest carbene, methylene. So it's a carbon with 2 hydrogens. And then again, there's a pair of electrons, right? And that pair of electrons would then be reacting. And this is just how you make that happen. Okay, so you take diazomethane, which is this one here. Okay, you use photolysis, so you would shine light on this. And what happens is you cleave, you have this resonance structure. So you can make this one, and then this one, the carbon-nitrogen bond will break. Okay, and when it does, it leaves the pair of electrons there. And then you have nitrogen gas, right, N2 as a side product. Now again, this is very non-selective. So this is not quite useful for us. If we use carbene, it's going to react with just about anything. So in organic chemistry, that decreases our yield. Okay, so this isn't really very useful for us. So what do we, or what can we use, is to take carbene and add 2 chlorines. So dichlorocarbene is really the reagent that you would see as a useful means, okay, of using this class of compounds. So again, you just kind of make them here. You take chloroform, trichloromethane, and then you react it with a base that we already know very well, right? Potassium Tbutoxide. All right. And so what that does again, right, is to remove, right, one of the chlorines. And you can see that it comes off as the salt. All right. And then you're also going to have to remove a hydrogen, right? And that's where the base comes in. That's what bases do. And then you end up with the dichlorocarbene. So this is how you make it. And that's really, again, the useful part. And this is called a carbenoid, excuse me. Because it's not, carbene is really with the hydrogens, but those aren't quite as useful. So this is dichlorocarbene, and this is what we can do. So we can react with a double bond, again, a an alkene, okay? And what happens then is you form a propane, cyclopropane, excuse me. So it's a cyclic. So the double bond, the electrons attack the carbon of the double bond, and then the pi electrons attack back. And then you form two new bonds, right? The one that was the nucleophilic attack, and then the pi bond bonds back to the carbon. So you end up with a cyclopropane, dichlorocyclopropane to be precise. Okay, so you can see that down here again, right? So this is going to be, right, the attack point. And again, this is chloroform in the presence of the base. Okay, that's going to form your dichlorocarbene. And then the dichlorocarbene reacts with the double bond to give you the dichloropropane. And this is a syn addition. Notice that the double bond, the wedges, right? The two wedges there means it's cis.
Where did the cyclopropane come from?
That's what I mean. The cyclopropane is formed when you form a new bond here, and then the pi bond comes and attacks it back, so you actually are forming two new bonds with the same carbons, right? There's 3 carbons involved, the 2 of the double bond and the 1 of the dichlorocarbene. So 3 carbons in a cyclic arrangement. So what's the nucleophile? Carbene, right? But what's the leaving group? The pi electrons, right?
Yeah.
Technically, by breaking that, right, that bond is acting as a pseudo-leaving group. It's not truly a leaving group. Nothing is leaving. But the pi electrons have to, right, that double bond has to break to make this arrangement possible. So then where do the pi electrons go? It doesn't leave, right, completely. It comes and binds to the carbon. So you're actually making 2 bonds at the same time. That's how you get a cyclic arrangement.
I'm just confused about the dichlorodiethylcyclopropane.
Yeah.
Dichloro.
Why is it propane?
It's 3 carbons, 1, 2, 3 in a cyclic arrangement. That's cyclopropane. Then these are considered substituents. They're coming off of the ring. So that's the diethyl part, 2 of them. And then you also have 2 chlorines as substituents, so that's the dichloro part.
So there's a little cyclo.
The cyclopropane is this part here, this triangle.
Then wouldn't that have like a cyclohexane added to it in the top one?
Cyclohexane.
Yeah, that's why.
This one here?
Yeah.
Yeah, this one, the double bond is here. There's no substituent really, just the cyclic remains, right, as a cycloalkane.
The name.
Huh? How do you name it?
The name.
Yeah, the name is just what
Yeah,
it
this
is.
is going to be tricky because this is a bicycle, and we don't learn how to name bicycle because it's a little bit complex. So you would have to name it cyclopropane and cyclohexane together, and it gets tricky. So we don't know how to name those. But this one, because it was linear to start with, it makes the cyclopropane, which then gives us substituents. But this isn't truly a substituent. The cyclopropane and the cyclohexane are part of the bicycle, and there's a naming rules for those, but we don't learn it at this level. If you're curious, you can go to IUPEC, or you can, draw this. There's some programs where you can draw that, and they'll give you the name online, free program. So if you're curious, but we don't learn those rules, so I don't want to confuse you and make you think you're going to have to know that. So no name for that one.
Or no one wants to carbene and not, or just put the 2 pairs of.
Yes. If it was on the exam, I would put the 2 electrons to make sure you knew.
Yeah.
Yeah, no, I would put it there. I mean, if you think about it, this carbon doesn't have enough bonds either, right? It really only has 2 bonds and 2 electrons, but they come together as a pair in the carbene. So looking at this, I mean, another clue is that carbon doesn't have enough bonds. It should have 4, and it only has 2 bonds and a pair of electrons, right? That's kind of wrong, right? Does that make sense? So, I mean, I would definitely put the electrons there for you so you would be clear. But if you look at the structure, it doesn't quite look right. There's only 3 groups, right? 3 things there. There should have been 4. So these are highly reactive groups. Okay? And then finally, I just done a couple more reactions here. So the Simon-Smith reaction, again, 2 chemists that came together in this work. So this is a way of adding the methylene. So let's say we don't want the chlorines there, right? Because when we do the previous reaction, the chlorines are always there, right? Because they come with the reagent, right? Let's say you don't want those chlorines, right? Okay, so here's a way of doing that. So this Simon-Smith reagent, which is really a zinc-copper couple, so that's it right here. So it's a zinc, okay, bonded to a copper. And then you are associating that with diiodomethane, so it's just like the dichlorocarbene here. Okay, you're going to generate this with iodine, but what ends up happening is this iodomethyl zinc iodine. So this is really the reagent. And so you can use that again as a organometallic compound. So what's going to be your nucleophile here? I know it looks crazy, right? But what should your eyes go to? Right? The zinc, the carbon attached to the zinc, right? That's really what's going to be reacting. Does that make sense? I know some of this stuff is, looks quite different from other things we've seen before, but and then what you end up with is cyclopropane, not the dichlorocyclopropane. So it looks like this. Again, here's a alkene, so you're starting with that. And then you're reacting the double bond, right? So what's going to happen, right? This has, right, the attack, right? And then the pi also attacks, right? But the iodine, because of the zinc, it forms a salt with it. It comes off. Again, no need to know this mechanism. It's complex. But this is really the key is having that carbon be able to attack, right? And then the pi comes back and bonds to the same carbon, and it forms the cyclopropane. And so here's a name for you. Like I said, there's its own rules for naming these. So don't worry about it. Right? But there's 7 total carbons. That's why you get heptane. Does that make sense? Right. Do you want to know or you don't want to know?
No.
Okay.
No, we're good.
Yeah.
Not on the exam, so don't worry about that name. But there's a clue to the name bicycle. So, and then again here, right, you have this starting material. Again, there's a carbonyl, which we'll eventually see how we can react to carbonyls. But right now, we're focusing on the double bond, right? So the carbon attacks, the pi bonds back, right? And you end up with your cis product. This is a syn addition, just like the previous reaction. Okay, and this is just giving you, again, those arrows showing you, okay? And then the key is that the zinc, right, picks up the iodine. So you get rid of that, the halogens here. With the chloride, that doesn't happen. So with this Simmons-Smith reaction, you can end up with just the cyclopropane. That's it. So like I said, it's a pretty short chapter. It's just an introduction. We'll see organometallics again in our other chapters. So you just want to be aware of what they look like in the general reaction, right? This nucleophile formation.